Welcome to the course on power electronics with wide bandgap devices. Today I am going to discuss about LTspice simulation for generating EMI noise in the converter. So basically I have already discussed about this different kind of EMI noises present in the converter. So how to generate this kind of noise in simulation? Generally what happens when we perform simulation, mostly the simulation is ideal in nature. But in LTspice that I have already discussed, we can actually see actual kind of behavior of the circuit. So if it is possible to see actual behavior of the circuit, so then we can also see the noises which are present in the converter. In order to see those noises, we have to simulate the circuit in similar way as the practical circuit is going to be. So let's see how that is possible to do. So as I have already discussed with you earlier, to import a device in the LTspice simulation. So how to import that device, that I have already discussed in details. So basically what you need to do, since we are considering this wide bandgap devices, we will be using this wide bandgap devices in converter. Last time I have showed you the boost converter. So then after that, how to simulate that converter to generate the EMI noise in simulation, that I will show. So you can see here, so this is like third party model. It is uploaded in the computer itself. So you can see the same device which I have shown you in the last lecture. So this third party model should have two files, as you already know. So selected switch is C3M01200065D, the similar switch, and the packages and everything remains same, right? So the same device we will be using. So next is that, so the silicon carbide based boost converter simulation is already shown in the LTspice simulation in last lecture, right? So now you can see, so the power level, supply voltage, output voltage, switching frequency, inductor current ripple, output voltage ripple, all remains same. So the converter simulation, it is shown earlier. Okay, so all the parameter, how to define different parameter and everything, that also I have already discussed. So this part already I have discussed in details. So once you consider this boost converter, then obviously you won't be able to see EMI noises, right? In order to consider the EMI noises in the simulation, what we need to do? The first thing is that we have to consider the parasitic components which are present in the converter. So if you see this particular boost converter, it is ideal kind of boost converter. So how the ideal kind of boost converter looks like? So basically whenever we are considering any ideal configuration, so then the converter is having one input DC voltage source, right? So which is considered as ideal. Obviously in simulation we cannot provide distance, so that's why it is connected next to the converter or close to the converter, and then there will be inductor of the boost converter, and then the switch which behaves as the ideal switch. But since we are importing the device, so then this switch we can consider as the practical switch. It is having all the parasitic which is required for actual circuit. Now switch is having all the parasitics, but this inductor and then diode and output capacitor and then load, right? So load resistance is considered here. So now this, all this you can see here, this is output, this is C out, this is L in, S and D. So all this component whatever I have drawn here, so they are all ideal except the switch, because switch part which we have imported from the particular device website. So that is already discussed. Okay, so this switch is having parasitic component, but this is having parasitic. But for inductor, diode, capacitor, they don't have parasitic component, and also the line is not having any parasitic component. So as I was telling, so this switch is having parasitic component, but the lines which are present, so generally what happens in practical application, the line which is connected here, they should also have some parasitic component. This line should have some parasitic component. This line should have some parasitic component. This is the line, there also parasitic component present. All this line will have parasitic component associated with it, because we'll be connecting different wires, right? And this inductor, diode, capacitor also will have parasitic elements associated with it. Now this voltage source, it can be connected next to the converter. That is very difficult to connect, but if it is connected long with long wires, so then that will also have some parasitics which can be considered in this particular place. Now this is with respect to the converter layout. Now with respect to ground, there will be parasitics, that already you know from the discussion of the EMI. So this part will have parasitics, again this part will have parasitics. So these are parasitic capacitances. So here you will see different parasitic inductance present in the circuit along with some resistances. So those things we need to consider for EMI noise generation. So the circuit layout of the boost converter that I am showing you here in this particular slide, which is having all the parasitic element. So you can see here, so in actual case, so between V in and the point here, so this point, so there is like parasitic is not present, but here L6, L1, R3, these three parasitic elements are connected, and not only connected, they are actually derived, means it can be also derived in calculation or in the like this. If you are using PCB, so from PCB track, what will be the value of this parasitic component, that can be derived. So actual value if you use, then you will get results more close to the practical result. Okay, now this is with respect to one particular part. So you can see here, so this is with respect to one particular part, so these parasitics are present. So between this point, so basically input and the switch, there is parasitic component L2 is present here, right? Now with like with respect to diode, so between diode and the point which is connected to the switch, so you can see here, so this is present here. So these are different components which are already discussed in the table, so that I'll tell you. Then you can see here this pulse generated for the gate drive. So there these different parasitics, or like you need to connect the internal resistance, so basically external resistance for the gate of the switch, so that along with the inductance which is also shown in this particular part. So now these are the different parasitics present. So let me just explain to you different parameters which are considered for this boost converter. So you can see here, so these are the different parameters. So LG is the gate inductance. So gate inductance, where it is, so this is the part where the gate inductance is present, right? So this LG, what is the value of this LG? This is 15 nano Henry. So this is again like how much it is going to be, that can be calculated, or that can be actually derived from the PCB itself. Okay, so now this is the value is connected here. Now LD, if you see, so the LD part is the drain inductance. So this, as I showed you earlier, so this is between the point which is connected input voltage and the switch. So the that particular path, it is having drain inductance of 12 nanohenry. Although these values are very small, it looks small, but for high frequency operation for wide bandgap devices applications, this is quite significant, and this plays very important role. For comparatively low frequency operation, where generally we use silicon devices, there this may not cause that much significant problem, but there will be problem. But like as I mentioned you earlier, so the EMI noises, if it is within the limit, then we don't have to worry. But if it goes beyond the limit, so that time we have to design filter, and then things will become much more complicated than that of the low frequency operation. So that is why it is very important to consider these small inductances as well. Although this is in nanohenry, but let's say you are operating the converter at megahertz level. So in that megahertz frequency level, this nanohenry becomes quite significant, and the uh, noises or whatever ripples will be associated due to these parasitics, they will play significant role in the power circuit operation. Okay, that is why we have to calculate what will be the values of these inductances, and then obviously in simulation we will see how much role they are playing, right? So you can see here, now this is LS is the source inductance, right? So this source inductance you can see here, so this is 12 nanohenry. So this source inductance here dot parameter LS, it is actually shown in this particular place. So you can see here it is actually mentioned here with L3, means between source of the switch and the circuit ground, not the actual ground. So this is circuit ground where it is connected to the negative point of the BC voltage. Okay. Now the Schottky diode lead inductance, so that is LSD, which is actually shown here. Now this lead inductance, what is this? Like there are different packages which are available for the devices, that I told you, like you can import the devices with like having like lead it is having significant length of the lead, or maybe lead length is small, or maybe is SMD kind of devices. So like any type of packaging you can select based on your application. Now as we go from SMD to the lead like TO kind of packaging, so then lead length will increase. So then what will happen, if lead is length is increasing, then it becomes easier for us to use that particular component in practical circuit, but that will cause additional parasitic elements to be present in the converter. So you can see here, this is Schottky diode lead inductance, that is 53 nanohenry. So due to presence of this lead, so although this lead length will not be much, but this 53 nanohenry you can see with respect to other inductances, it is quite significant, right? So probably if we can choose SMD in place of this kind of packaging, so then this inductance can be reduced, right? So if it is significant for your converter, then you can choose different packaging. So it is up to you. Now L loop is the loop inductance. So you can see here, so the loop inductance, it is actually shown here as the 52 nanohenry. So this 52 nanohenry is due to the connection of this input voltage and the part where it is connected to the circuit. Generally we consider this voltage is actually very close to the circuit, so there will be no problem, but generally there will be some inductances and resistances associated with it. So this is the loop inductance which is shown in the table. Now all these parameters are actually defined in the simulation itself, in this like different values whatever is given in this, so they are actually shown. Now these inductances are described in the table. Along with inductances, generally there will be resistances. So resistances actually it is not connected in other parts of the circuit, it is connected here. Resistance will not cause any problem of the noise, it will cause power loss. So that is why if we want to see the noise, then the resistance part will not play the significant role, right? Because inductance, capacitance, those will play significant role in producing noises. But if you want to calculate the efficiency, so that time this resistance plays very important role. So that time you have to connect different resistances in order to find out what will be the power losses. Even the resistance of the inductance, so the main inductance what is present in the circuit, so basically this is the inductance, main inductance L, which is shown here. So this inductance will have some resistance, so this resistance can be defined here, or maybe along with the line that can be shown in one place. So this resistance can be inductance, resistance of the inductance, or maybe due to path also there will be resistances that can be added here. So the total resistance can calculate what will be the power losses in that particular path. Okay, so these are the different things which are considered in this particular simulation. So now if I go back to previous diagram, so the same diagram if I try to now draw with considering different parasitic elements, so you can see here, so input it is present, so this is the ideal circuit, right? Now here then V in, we have same V in, along with it we have loop inductance, so L parasitic, so I'm just giving you parasitic one. Then main inductance, so that is L in, as the name is given here. Along with it one resistance is considered, that can be part of this inductance R, inductance L in, this R is considered. Then this is, you can see here there is a connection to switch. So now in this path there will be parasitic inductance, right? So let's consider this is a parasitic 2. I'm just writing this different name just to give you ideas to what are the different parasitic components are connected in this particular circuit. So now this switch is having, so drain, gate and source. Now source also will have some parasitic inductance, L parasitic 3, right? Now this is connected to diode, so diode is having another parasitic inductance. Okay, so this diode which is connected D here, and this is connected to output capacitor which is C0, and then this is connected to load. And here gate pulse is generated. Ideally the gate pulse should be connected directly to the gate itself, but there will be another parasitic in this particular path 5, and then internal resistance of the gate, so that will be there, so Rg. So you can see here the same circuit, same ideal circuit is now modified, means in simulation the ideal circuit is simulated and showed earlier. Now this practical circuit is considered for simulation purpose of EMI. There these different parameters are added mainly. So R, R you can add or you can remove, so that is up to you, that's not a problem. So these are the different parameters are considered. Okay, so this is what is shown in this particular page in the simulation. Okay, the switch model you can see here, so this you can import directly from the website, right? And Schottky diode model which is imported, means this switch and diode itself they have their own parasitic component. Means if you consider the switch which is ideal, maybe which is present in the library of the LTspice, or if you are using different software to see the simulation, so there if you are adding that ideal switch, so then you have to add parasitics of the actual switch by considering the datasheet. But if you just import, it is already considered everything which are given in the datasheet. So then these are already included. That is also like earlier only we have considered this switch model in boost converter simulation, but here we are also considering the Schottky diode model for this EMI simulation. So let me just open that EMI simulation. So basically simulation of this particular boost converter along with parasitics, that I'll just open in LTspice to show you how the simulation looks now. So now you can see here, so you already know how to like write different parameter in this particular window. So how to like build a circuit in LTspice, that you know. So this you can see here, this is the switch model which is like first imported and then used in the converter. This is the diode model which is given in the which we have actually used. So you can use different diode model, that is not a problem. Okay, so now all this like different loop inductance, actual inductance, parasitic resistance, this drain inductance, source inductance, gate inductance, all these are added, and these are added, these values are already given in the table. The same values are used in the simulation purpose. This is the input voltage and this is the gate pulse voltage. So now let's run the simulation to see what we can get. So obviously you have to configure this analysis. So stop time is given, time to start saving data same as the previous case, so that is also given. Maximum time step is given 10 nanosecond. So this you can choose. Now the simulation is running. So because we have considered many parameters, so it is taking some time. So you can see this like how much percentage of the simulation is done, which is shown like in the bottom. So here you can actually add any other parasitic element which you think will be present in the converter, and that will obviously give you much more practical results. So you can build actual circuit what you can see in the experiment or the hardware, how it is going to be. The similar kind of circuit you can just build here to see what kind of noises will be present. So this will give us the clear idea like how these noises are going to be. Okay, let's see the different points in the converter. So you can see, you know, like how to see the current. So you can see this is the voltage across the switch. So you have to connect two different. So you can see here, so as you are seeing voltage across the switch, so this particular you can see along with current. So current of the switch you can see here, so that you can actually see the particular point, so where this switch is actually changing the state, means like either turning on or off. So this turning, so basically voltage of VDS, voltage across the switch is shown is the upper one. So here you can see this particular point, here you can see this is basically the noise part which is available here. So this you can actually zoom in and to see what kind of noises are present. So you see this is the kind of noises are present in this particular converter during the turn off time, right? So you can see the current is also turning off. So this is also having some kind of oscillation. Here it is having some oscillation in the voltage. After some time this voltage is settling down. That depends upon like the circuit condition, like how much time that oscillation is going to be. It, this oscillation actually tells you there is like different energy storage element are present as parasitics. So this is LC kind of components are present. So C obviously it is taking the parasitic of the switch, so which is like inbuilt to the switch, like input capacitance, output capacitance, reverse capacitance of the switch, and L already added in the network. So that is giving us this kind of oscillation, right? And the frequency of the oscillation, that if you want to really calculate, so that can be also done from the L and C of the actual network. The similar way generally we calculate this, like what will be the frequency of this like different LC parameter based network, right? And also like depending upon the damping factor, so that how much time it will take to settle down, so that part can also be visible. Now similar thing you can also see during the turn on time. This is the turn off time. Now turn on time, if I zoom in the circuit part, so there you can see there, so this part you can see here, it is like similar kind of oscillation it is visible in the current. Earlier during the turn off time, it is the similar kind of, this kind of oscillation was visible in the voltage, and during turn on time it's a similar kind of oscillation it is visible in the current. Obviously the magnitude will be different depending upon the current magnitude and the voltage magnitude. So this kind of oscillations are visible. Now, do you remember this actual boost converter simulation results? So let's just see the ideal kind of boost converter simulation results, whether it is really present or not, and how different it is in ideal boost converter. So let's just open this ideal boost converter simulation. So this is the ideal boost converter. Let's just run the simulation. So because you know like the parameter and everything remains same. So here only the switch element is the actual element. Remaining others are ideal kind of element. So here also the resistance is added in this. And this is the voltage, and then let's connect the current part also. Okay, let's see this together. So if we have, so let me just show you in different window, two different windows, so it will be visible to you clearly. So now you can see this, the top one is the voltage of the boost converter and bottom one is the current. Now if we zoom in the turn off part, so that this is the part, so where this is the turn off is happening. So if we zoom this part, you can see this is the clear waveform. See, I mean it is already having turn on and turn off due to the presence of this parasitic capacitance of the switch, but it is not having the oscillation which is visible due to presence of parasitic inductances in the circuit. So this is during the turn off time. It is clear kind of waveform. It doesn't have any oscillation. So this clear waveform is not what we can see in the practical circuit. In practical circuit, the oscillations are visible, similar to the simulation results which you have just seen with parasitic elements. Now see the turn on time. So turn on of this, it will also be very clear. So see, this is the turn on part. Very small oscillation is there, like here in this particular portion, that is due to the capacitance. And if the switch is having any inductance inbuilt to the switch, due to that, but not due to the parasitic inductance in the converter path, right? So this is also kind of, you can say, clean kind of waveform, but this is not what you can see in the practical circuit, in the practical operation. So that is why like this is good for a basic understanding of the network, how the circuit should behave, but this is not useful to generate or to see the noise level present in the circuit. That time we have to consider the practical circuit. Then only we can design filter and we can see, we can expect the noises which are generally present. Okay, let's just close this particular window, because you know this already you have seen. You, if you want, you can try at home to see this kind of noises. Okay, this is the one which is with the parasitic element. Okay, let's see other parameters which are present in the circuit. So if you want to see the diode voltage and current, so that is also possible to see here. This is the diode voltage. This is also having noises. And the diode current, this is also having noises similar. So these are the different kind of noises which also you will be able to see in the practical circuit. If you get to see this, then you have to again go back in the analysis of the circuit part to understand what are the parasitic component may be present. Add those again in the simulation to understand the circuit operation better. Okay, now close this window and then, okay, just let me open the PPT part. So with this you can simulate the network. You can use different switches. So this is actually the silicon carbide switch. You can use gallium nitride switch also to see this simulation further of how much noises will be present in GaN based circuit. You can increase the switching frequency to check if the frequency is increasing, how this different noises is going to be. You can start with the frequency where we generally use silicon devices, let's say 10 kilohertz or 20 kilohertz. You can go till megahertz to check how these noise levels are varying. This will give you clear idea how these parasitic elements is having significant role as the frequency is increasing. Okay, so now that was with respect to different parasitic element of the boost converter. Now in this, what we need to do in order to see the noises? So basically first we have to design the practical circuit, then we have to connect LISN. Remember LISN, that line impedance stabilized network. So basically line impedance stabilized network, it is, so I have already discussed dual LISN. So generally it is having characteristics, so it is not characteristics, it is having the configurations like this. So here it is like there can be resistance, small resistance can be connected along with the capacitor, or if you want you can just directly connect this capacitor, this C1 and C2 with the ground. Similarly here also, like you can connect capacitor, small capacitor, or you can just directly connect the resistor part. Now okay, C3, C4. Now this point will be connected to 50 ohm resistance. This point be connected so there we can measure or we can see the noises. Okay, so now see the previous circuit, this is the same thing is actually shown here. So here you can see the LISN. So basically these are the different parameter which are connected to the boost converter as the parasitic parameter, as it is discussed in the previous slide. The same parameters are given. Along with it, this line impedance stabilized network is added. So in practical boost converter, this line impedance stabilized network is added, LISN basically. So in with respect to LISN, so this here this different capacitor and resistors are connected. So if you want to consider each arm, so there are like two capacitances, two resistances are connected, and then two inductances are connected with respect to positive and negative path. So basically four capacitances, four resistances are added, and two inductances are added to measure the EMI noise. So this is with respect to line 1, this is with respect to line 2. So this line 1 and line 2 we can measure if we have dual LISN. So this is dual LISN that already I have discussed earlier. So if you use single LISN, then you will not have the parameter with respect to each line, right? So each line information we needed. So these are the different parameters value are listed here in the right side. Okay, so now this need to be simulated in order to see different noises. So let's see in the simulation how this can be simulated, right? So you can see here earlier this input voltage, it was connected in this particular point, right? So let me just tell you here in the drawing, so it will become clear to you. So earlier what was the situation? So just right. Now this is connected to the load. Which is connected to the input. And this part which is drawn in black lines, see, this is the LISN. This is the part is added for the measurement purpose only. It doesn't have any other purpose. It just measures the noises present in the circuit. And these noises can be only plotted if we have parasitic component based network or the actual network. If we have ideal kind of network, it is not possible to measure this, right? These parasitic components only, this will give us the idea about the noises which you have already seen in the switching waveform. In the switching waveform you have seen in the ideal circuit there is no oscillation, right? But whenever we are adding these parasitic elements, there are oscillations. Now these oscillations are part of it this is like part of it coming from the parasitics which are present in the network. Another thing is that with respect to ground there will be parasitics, part of it coming from there, and these all are like kind of part of it is kind of due to the EMI noises. We can consider it as EMI noises. So that is the part of we are going to see how it is visible in the actual network. So this parasitic inductance based boost. Okay, so this is the circuit is shown in the simulation. So let me just open that simulation back again. Okay, so this simulation you can see here. So this is C4 here you can see this is CLISN. So whatever LISN 1 with respect to leg 1, so this is you can consider as leg 1. LISN 2 and R2, so this is with respect to leg 2, and LISN for positive and negative path they will be same. So you can see here, so this is the CLISN 1 with respect to leg 1, so this is 8 microfarad. CLISN 2, this is with respect to leg 2. So in leg 2, this capacitance value is very small. So basically, so this capacitance you can also neglect. So this is, you can see, 250 nanofarad. So now parameters with respect to RLISN 1, so this is 5 ohm, and RLISN 2, it is 50 ohm, and then L is 50 micro Henry. Okay, so now let me just open this. You can see here, this is 50 micro, this is 50 micro, right? This is 5 ohm, this is 50 ohm, this is 250 nano. And C2, just C1 and C2, let me just open this. So C2, you can see from here, this is, sorry, see this is 8 micro, right? Sorry, this is actually 5. You can see this. So now if you see this 50 like micro Henry inductor in both the path, they are same, but line 1 and line 2 inductance and resistance values are different. So the equivalent circuit, it becomes, so basically this capacitor, although it is connected, the equivalent circuit of it becomes, so basically there will be inductor with respect to this path, and then this goes to the boost converter. This is the so with respect to capacitance in the second part, in resistance is dominating. In the first line of LISN, basically the capacitance is dominating with respect to the resistance. So this is the part of equivalent part with respect to the LISN that is added to the boost converter. Is it clear to you? So now let's go back to the simulation file to show you the simulation. Okay, so this is the circuit. So this other things remain same. This is the loop inductance, this is the main inductance, resistance with respect to main inductance. These are the different parasitic inductances, gate resistance, actual switch, actual diode. This is parasitic of the source, output capacitor, output resistor. So let's run the simulation. Okay, and another important thing added here in the simulation. So this I haven't shown in the path. So this is the capacitance with respect to the actual ground. So this needed to be added. This is very important part. Equivalent capacitance is added. Generally, like set of capacitance need to be added. Okay, let's go. This is 100 picofarad. Okay, so let's run the simulation and see how this is visible. This will take some time. So you can check what will be the parasitic capacitance value which is connected here. So this is only one capacitance is connected. You can connect different capacitances with respect to this negative path, positive path. That is possible, or equivalent capacitors you can connect. And what will be the value of this capacitance, that also you can calculate and then connect. You can get different differences also with for EMI. Okay, this simulation is complete now. Now how to see this? So let's see the voltage of the switch first. This is voltage of the switch and this is current of the switch. So let's see how it is now visible. So let's see the turn off path. So this is the turn off. So you can see, so more oscillations you are able to see now. So you can see different oscillation. So the oscillations of the parasitic circuit is present here. Okay. So now see the turn on part of this. So you can see this current peak is very high. See, it is much higher than the previous case also. See this peak value of the current, it is very high in this case. Then it is settling. Like now see, if you want to choose any device, if the rated current of the device is required like 4 ampere, so as it is given here, so like settling to 4 ampere during the turn on. So now due to peak it requires 8 ampere switch. The switch value, basically rating of the switch, current rating, you have to consider much higher. Means if you consider just the rated value which is required for the design, that will not solve the purpose. Due to the presence of the parasitics, you will have this kind of different oscillations or the transient component present in the practical circuit. Here whatever you are seeing, let's say it is close to, now peak is close to 8 ampere. In practical circuit you will get bit higher, because you know in practical circuit some more parasitic component which probably it is difficult to calculate may be also added. So it will be close to like let's say 8 or little bit higher than that will be there. Okay. Okay, now in order to measure, so you can see this LISN1, VLISN1 point is shown here, VLISN2 is shown here. So this is with respect to line 1 and this is with respect to line 2. So you remember how we have calculated this common mode and differential mode noises. So common mode noises generally we have added line 1 and line 2. Differential mode, it is the differences of the current between two lines. So let's see how these different noises are visible in this case. So this is with respect to LISN line 1 and this is with respect to line 2. You can see here, so this is just for your reference, this drain voltage is shown here. So instead of drain voltage, let's just add the gate voltage part here. See, this is the gate voltage which should be actually like a square wave, but due to presence of the parasitics it is not like a square wave. It is also having some peak here. So if I just try to zoom in this particular part, see there are oscillations due to parasitic inductance presence in the gate path. And obviously there will be some turn on delay due to like the capacitance, input gate capacitance. And now this input gate capacitance along with the parasitic inductance, that gives this kind of oscillation. This is like basic LC network. If you simulate basic LC network and try to analyze the network with RLC, which is having the pulse kind of input, you will get this kind of behavior, right? Okay, so this is the part. So let me just show you the complete thing now. So see the LISN1 how it is going to be. So it is having like different positive and negative component, and LISN2, so the line 2 is also having positive and negative component. So this voltage level you can see this is like much lower. Okay. Now this two noises, if you add, then what you will get, that already you know. So actually you have to write down the formula of these noises, how you are adding. So then you will get the noise like this. Okay, now there also you can see noises FFT. Okay, if you see this, so now you can see this noises, right? So the maximum value, it is reaching near to 40 dB. So the noise spectrum you were able to see. So the different frequency level you can see at the bottom. So the magnitude you can see in the left side in dB, right? And the frequency level you can see in the bottom. So initially it is starting, so you can see here, so this is 100 kilohertz. So as it is increasing the frequency, the noise level is reducing. So the lower frequency, the noise level is bit higher. So then, like, if it is within the limit, cutoff limit, so then, like, whatever standards are given, so that standard you have to see. And there, as you know, CISP are different standards, like class 1, class 2, class 3, class 4, class 5. With respect to that, what is the maximum noise is allowable, that can be calculated, or that is given. So you just need to check whether it is above or below. If it is within the limit, you don't have to design filter. If it is above, then you have to design the filter. Like how much above it is, that you have to check. So let's say the limit is 20 dB. So if it is 40 dB, then you have to design filter for 20 dB, 40 minus 20. If the limit is 40 dB, then you don't have to design filter. Design filter, but we'll see later. Now let's see the other noises. So this is with respect to the addition of these two different noises, and the subtraction also you can see here. This is the with respect to subtraction part. Okay, so you can see by subtracting the noises is much higher. So if we have the limit 40 dB, so here it is like much beyond 40 dB. So obviously we have to design the filter. The maximum peak is reaching 120 dB. So that is around frequency, let's say 10, around 15 kilohertz frequency in that particular level. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So basically it is around 20 kilohertz in that particular level. So that in that frequency, you, if you are getting that noises, you have to design the cutoff, you have to actually design the filter with respect to that particular frequency, right? Then you have to add the filter and then check whether you are getting noises within suitable level or not. So you should be getting this kind of noises. When you add LISN, you should be able to see the noises. In order to select, you have the line 1 and line 2, you can check the line 1 and line 2 separately. You can get line 1 and line 2 FFT also, but that will not give you common mode and differential mode noises. Common mode and differential mode noises, if you want to see, you have to either add or subtract. So that formula, as I have discussed earlier in the EMI noise class, that you can refer, and then accordingly you can see the noises. You have to see the FFT part in the simulation, so then only these noises will be visible. Now go back here. So you can see, so this is the same thing, it is shown here. So this is conductive noise formula, it is given like this. So the same thing, it is actually shown earlier. So you have this line 1 and line 2, right? So this line 1 and line 2 are added, divided by 2, it will give you conducted noises. Only thing is that here you have to choose this part, so under FFT. that function, right? So that already is shown in the video, that you can check by yourself. Now similar thing you have to see for the differential noise. So the differential noise, this kind of spectrum is visible. So there it is LISN 1 minus 2 divided by 2. This is the differential mode noises, you can check. Okay, so now you can see whether this is the within the limit or not. That limit you have to see from the CISPR limit. Now that standard also you have to see whether you want to select class 1 or class 5. Based on that you have to design filter. Okay, so now you have to consider filter in order to reduce this. So now these are the parasitic element, these are the devices. Now we have to use the filter. We have input DC, we have LISN, right? So the LISN simplified version, how it looks, it is nothing but this capacitor, inductor and resistor, right? This is LISN part. This now if you have to design filter, so then what you have to do, you have to connect filter here. If you have to use filter, then comes your practical boost converter. This is the load part. Okay, EMI okay. This is a whole setup. So the filter designing part I'll be discussing in the next class. That's all for today. These are the references. Thank you.